This is going to be a brief equation review video for the magnetism exam. So this is the AP Physics formula sheet that you get from me on tests. And if you take the first page and scroll down to the bottom, we've got the equations for magnetism right here. The first equation is for a charged particle moving in a magnetic field. So if I've got, say, a magnetic field this way, and a charged particle comes in to the field with a velocity that way, and we're just talking about one particle, maybe a positive particle, the magnitude of the force on the particle is given by QVB sine theta. You use that one a lot, and you should know it. However, if instead of a particle, if I put a wire here and run a current through it, then I would use BLI sine theta right there. Or I think I told it to you F equals ILB. The order doesn't matter, multiplication is commutative, but a wire in a magnetic field, ILB. Now, neither of those equations work if the velocity of the current is parallel to the magnetic field. So if our velocity was this way, you can't cross those two vectors, so no force. If the current were this way, you can't cross those two vectors because they're parallel, so no force. Be sure to note the difference between force and field. If a problem asks you for a force, it's asking for FB. If it asks you for the field, magnetic field, it's asking for B. The equation for field from a current-carrying wire, so maybe you're asked about two wires near each other or a charge near a wire, and you need to find the magnetic field on the wire. You use mu naught I over 2 pi r. And that's a pretty simple one. You just plug in the current, I, and the distance from the wire that you want to know the magnetic field, r. The flux equation, sometimes written phi m, sometimes written phi b, just magnetic field times area, and if there's an angle between your surface and the field, then cosine theta. But we want our surface to allow the field to pass through it. So when we've got a loop and the field passes through like that, that's actually no angle. So that looks like perpendicular. We consider that no angle. And so if we rotate from here, this might be the easiest way to think about it, this is where we're measuring the angle from. So we're measuring the angle from where the loop would be perpendicular. Now you've had lots of practice with this. You know you need the magnetic field passing through it, so that shouldn't be too hard. We would consider what I'm about to show you to be, we're at the cosine of 90. So if our loop were kind of pointed like that, so that there's no field passing through it, that's when we would use the cosine of 90 and get 0 out of that. But basic idea you've used before, phi is magnetic field times area. So flux is magnetic field times area, finding the flux with that equation. Next we have induced EMF. This equation is for a single loop of wire. I give you the more general one with the N for if you have more than one loop of wire. And they went ahead and determined a direction and put a negative phi m over delta t. So if you go from a lot of flux to zero flux, you end up with a positive voltage. If you think about that, because it's final minus initial. So if your final were 0, the negative that they've stuck in there lets you go ahead and have the positive voltage out of it. But not really important to remember or make a distinction. If you can do n phi b times or over delta t equals EMF, you're good. And the special case for a rectangular loop of wire traveling at a constant velocity through a magnetic field, or in or out of magnetic field, BLV is your induced EMF. You already know all these equations and used them before, but that's just a quick reminder of each of them. You should have all of those memorized when you come in on Monday for the multiple choice section. Also, you're going to need equations for Ohm's law, because if you're given an EMF, remember that the EMF is just a voltage, and so if you want to define current, you could then divide by the resistance. You'll also need to remember force from a magnetic field, because you might be asked, how can you get a charged particle to travel straight through a magnetic field? And so you might be balancing a magnetic force and an electric force. Now remember, the fields don't balance. You don't set the fields equal to each other. It's that, let's say if we have a magnetic force this way, we would need to have an electric force the other way for a charged particle to travel straight through the area with magnetic field. So the electric field equation is solved for E, but you can easily rewrite this F equals QE. So remember, force from an electric field is F equals QE. Well, they probably won't be in the multiple choice section. You will probably have to use, or may have to use, a kinematic equation at some point on the free response section. So remember those, quick refresher. Also, since we deal with centripetal force and acceleration, that's centripetal acceleration, which means centripetal force is mv squared over r, stuff you've done before. And don't forget about Newton's second law. Net force is mass times acceleration. Okay, so those are the equations that you will want to know for the exam. You've used all of them. Hopefully nothing was new to you here.